Hello and welcome to the notes about shifting equilibrium when something changes. So we learned last time about equilibrium and how reversible reactions will basically even out over time so that they will be at equilibrium. And equilibrium is where the concentration of the products and the reactants stop changing. Right here. We know that it doesn't matter where the concentration started. It will all go to the same equilibrium concentrations for a particular reaction at a particular temperature. We also know about K, the ratio of products to reactants at equilibrium. And that K is really the thing that determines, how many products compared to how many reactants. So we might have a really low concentration of products and reactants or really high concentration of products and reactants. We just added a bunch more. But K, the ratio, is going to be the same. So at equilibrium, the products and the reactants are balanced. They might not be equal to each other, their numbers or their concentrations, but each individual concentration is staying steady, and the rates of the reactions are equal. But today we've got to talk about when something changes. If all of a sudden we're off balance. So let's go back to a familiar simulation. It's at equilibrium. In the strip chart down here, we can see that the products and the reactants, each one is staying pretty steady. It goes up and down a little bit, but pretty flat. But when we add a bunch more reactants, we can see that those concentrations go way up, the red and this aqua line. But the concentration of the products stay steady. We didn't add any more. But if we let it react, what's going to happen is we are going to go back to that equilibrium ratio. The aqua and that red line will go back down, blue line goes up, and we're back at K, the ratio of products to reactants being the equilibrium ratio. So in most cases, if we've got something in equilibrium and we do something to it, it's going to do its best to get back to equilibrium. Chatellier's principle tells us a little bit about how it will do that. What it says is that the forward or the backwards reactions will adjust the rates until the change is balanced. So for example, in the reaction we just looked at, when we first started, there was a lot of reactants. So the reactants were bumping into each other, and the rate of forward reaction increased. And so then we started getting rid of reactants because they were reacting and forming more products. And eventually we got back to equilibrium. But both concentrations were higher than they had been before. But the ratio was back to equilibrium. So just like the one we just saw, some reaction shifts keep that same balance, that same ratio. There's a few that don't. We'll talk about them in a little bit. So the ones that do are really about adding or subtracting products or reactants. So we can add the reactant, we can add product, we can subtract a reactant or subtract a product, usually by reacting it with something else. And so let's look into this a little bit more. System and equilibrium. Notice the concentration of reactants and products is not the same. That's perfectly normal. It can still be at equilibrium if the rates of reaction are balanced. So for this example, what do you think about K? Well, there's more reactants, so K has got to be less than 1 because the denominator is larger. Okay? Well, we added a bunch of reactants. What do you think? Way too many reactants. We're not at equilibrium anymore. So we've got to adjust, and we're going to do that by increasing the forward rates of reaction until the ratio is balanced again. So let's look at this in a little bit sort of less chemical way. Imagining a school where we've got boys, we've got girls, and boys and girls can date each other. This is a very sort of old school where the rules just work like this, no other way. But the couples can get together and they can break up. And so at the beginning of the school year, everybody's single. Looks like at this school there's a tiny bit more boys than girls. But pretty quickly they start getting into couples. And some of the couples break up and more couples form. But by, midway through the first semester, we're pretty much at equilibrium. The number of couples compared to the number of singles isn't really changing. Certain ones are breaking up and getting together though. So midway through the quarter, we get 50 new girls joining the school. What do you think is going to happen? Let's look. Well, what happened? Wow. Okay. The couples increased. That makes sense. The number of boys decreased, the number of girls decreased because we had to take somebody to make those couples from. And so the key thing is that if you look at it overall, we added a reactant, the forward reaction increased, the products increased, and the overall number of reactants decreased from where we added, but still higher than where it started, the overall. Okay, so let's look at a more chemistry-related example. We've got an initial equilibrium. We add a bunch more of one of the reactants, which then starts reacting. And so we start making more products. And here we go. Got more products than we started with. Even A, this new particular reactant has gone down, and the other reactant has also decreased. Again, to keep that equilibrium, that K value, the same. So similarly, we talked about adding reactants. You could, of course, add products. It's the exact same thing, but from the opposite side. But if we decrease a reactant, the reaction will shift to make more of it. Look at this example. Girls start dating boys from other schools. Some of the couples start breaking up, and we get a little bit more of the singles forming to make up for those that kind of got taken out. So we have two other changes that don't just sort of change the number or the concentrations, but actually affect that ratio of products to reactants so that it becomes different. And the first of those is changing pressure or volume. So an example is the reaction where iodine gas, single molecule here, goes and breaks up into two separate gas molecules of iodine. And I forgot to put the two here, but you can see that if you look at the smaller one, that you've got one molecule over here turning into two single atoms over here. And if we look at the reaction, PV equals nRT, we can see that if we change pressure or volume over here, we're going to change N over here. We have to in order to keep this balanced. And so if we increase the pressure but are keeping the same volume, we have to have the number of, if we increase the pressure and usually by doing that we've decreased the volume, the number of moles is going to have to decrease in order for that to happen. Okay. And if we decrease the pressure, basically give it more space to spread out, we're going to be able to create more molecules, if that's a possibility in the reaction. And so we'll favor the species that there are more moles of gas. The next one is a change in temperature that also will change the ratio. So remember, if there's one reaction that's endothermic, the reverse reaction is exothermic. Because it's going, one direction is going backwards, exact opposite. So an example is this reaction where nitrogen gas and hydrogen gas react to form ammonia. It's an exothermic reaction going forwards, which means it's an endothermic reaction going backwards. Okay. And I put these releases heat and takes in heat because I think it helps us remember what happens next. Okay? So if we go forwards, we're releasing heat. If we go backwards, we're taking in heat. Okay? So let's now imagine we're heating the reaction. Well, we've added heat here. That heat has to go somewhere. We are going to increase the reverse, the endothermic reaction, and the ratio will shift to form more reactants. In the opposite case, if we cool it, well, we need something to sort of release the heat. It's definitely not going to be, the endothermic reaction is not going to work too well if it's getting very cold. So the exothermic reaction is going to work more, and we'll shift it to forming more products. So let's just summarize. If we change something in an equilibrium reaction, it will try to go back to find equilibrium again. Okay, Le Chatelier's principle is a thing that talks about this, and it's really about the rate of the forward or backwards reaction increasing, depending on what best balances the changes. So we could change the number of reactants or products, and if we've got more reactants, we're going to react those more. If we've got more products, we're going to react those more, which is then going to move it to the other side. We can change the pressure. Okay, if we have more pressure, it'll react, sorry, I messed up this one, it'll react to make the side with less moles. Okay, please, let's cross this out. Less. Can't write the rest of it, but less moles. Okay, and if the pressure is decreased, it'll react to form more moles. Okay, and then the next one, last one, is we change the temperature. If it'll favor either the endothermic or the exothermic reaction, depending what the temperature change is. Okay, so that's it. Look back at the simulations as well, because I think that really watching and seeing this in practice helps a lot in understanding. Thanks.